Embedded systems are the silent workhorses of the modern world. They are in our cars, our appliances, and even in our pockets. These systems are designed for specific tasks, often with limited resources. One crucial aspect of developing efficient embedded systems is understanding and effectively using data types. Data types determine how data is represented, stored, and manipulated within the system. Choosing the correct data type can significantly impact an embedded system's performance, memory usage, and overall efficiency. Conversely, using inappropriate data types can lead to performance bottlenecks, increased memory consumption, and even system instability. This essay delves into the critical world of data types in embedded systems. We will explore the fundamental types, their properties, and the importance of selecting the appropriate type for specific tasks. Furthermore, we will examine advanced techniques like fixed-point arithmetic and data type optimization, providing you with the knowledge to write highly efficient embedded software. Embedded systems operate within a tightly constrained environment compared to general-purpose computers. These constraints stem from the need for low power consumption, small size, and cost-effectiveness. Memory, both volatile, RAM, and non-volatile, ROM, is a precious resource in embedded systems. Choosing a data type that exceeds the necessary storage requirements can quickly deplete the available memory. This is particularly critical in smaller embedded systems where memory is extremely limited. Similarly, processing power is another constraint in embedded systems. Complex data types, or those requiring extensive computations, can burden the processor, leading to slower execution speeds and increased power consumption. Therefore, understanding the resource limitations of your target embedded platform is crucial. This understanding, combined with a thorough knowledge of data types, allows developers to make informed decisions that balance functionality with resource efficiency. Data types are the foundation upon which all embedded software is built. They dictate how the system interprets, stores, and processes information. At their core, embedded systems typically utilize a set of fundamental data types that mirror those found in general-purpose programming languages. These fundamental data types include integers, floating-point numbers, and characters. Integers represent whole numbers, both positive and negative, providing the basis for counting and arithmetic operations. Floating-point numbers, on the other hand, are used to represent numbers with fractional components, enabling calculations involving decimals and real-world measurements. Lastly, characters are used to represent single letters, symbols, or numerals, forming the basis for strings and text manipulation. These fundamental data types are the building blocks for more complex data structures and algorithms used in embedded software development. Each data type comes with a set of properties that determine its characteristics and suitability for different tasks. Understanding these properties is essential for selecting the optimal data type for a particular operation or variable. The key properties to consider are range, precision, and memory footprint. The range of a data type defines the minimum and maximum values it can represent. For instance, an 8-bit signed integer has a range of -128 to +127, while a 16-bit unsigned integer can represent values from 0 to 65,535. Precision refers to the level of detail a data type can store, particularly relevant for floating-point numbers. A floating-point number with higher precision can represent smaller increments between values. Lastly, the memory footprint of a data type indicates the number of bytes it occupies in memory. This property is especially crucial in embedded systems where memory resources are limited. Section 5. Selecting the right data type. A design decision. Choosing the appropriate data type is a critical design decision in embedded systems development. The selection process involves analyzing the data itself, understanding the required operations, and considering the constraints of the target platform. The first step is to determine the nature of the data. Is it discrete data like event counts or sensor readings, or is it continuous data like temperature or pressure measurements? Next, consider the range of values the data is expected to fall within. Selecting a data type with a sufficient range prevents overflow errors, which occur when the value exceeds the data type's maximum capacity. Finally, analyze the required precision. If the application demands high accuracy, such as in scientific calculations or sensor data processing, a floating point data type with sufficient precision should be used. Section 6. Case Studies, Real-World Implications of Data Type Choices. To illustrate the real-world impact of data type selection, let's consider a couple of case studies. Imagine an embedded system controlling a motor's speed. Using an 8-bit integer to store the speed value might seem sufficient initially. However, if the motor speed needs to be adjusted in fine increments, the 8-bit integer might lack the necessary precision, leading to jerky movements. In this case, a floating point data type or a fixed point representation would provide smoother control. In another scenario, consider a battery-powered sensor node transmitting data wirelessly. Choosing a data type with a smaller memory footprint, such as a 16-bit integer instead of a 32-bit integer, can significantly reduce the amount of data transmitted, conserving power, and extending the node's battery life. These examples demonstrate that selecting the right data type is not merely an academic exercise, but a practical consideration with tangible consequences for an embedded system's performance, efficiency, and overall functionality. Section 7. Advanced Data Handling, Optimization, and Emerging Types. As embedded systems become more sophisticated, developers are constantly seeking ways to optimize data handling for improved performance and efficiency. One such technique is data type optimization, which involves using the smallest data type possible without sacrificing the required range and precision. For instance, if a variable is known to hold only positive values, using an unsigned integer instead of a signed integer effectively doubles the positive range within the same memory footprint. Another advanced concept is the use of custom data types or structures. Structures allow developers to group related variables of different data types under a single name, improving code readability and organization. This is particularly useful when dealing with complex datasets, such as sensor readings or network packets. Furthermore, emerging data types like bool and enum are gaining traction in embedded systems development. The bool data type represents Boolean values, true or false, and is particularly efficient for storing flags or status indicators. Enum, enumeration, allows developers to define a set of named integer constants, enhancing code readability and maintainability. Section 8. Fixed point arithmetic precision where it matters. In certain embedded systems, particularly those dealing with signal processing or financial calculations, achieving high precision in numerical operations is crucial. However, using floating point data types while offering high precision can be computationally expensive and resource-intensive for some embedded platforms. Fixed point arithmetic provides an alternative approach to handling fractional numbers with a balance of precision and efficiency. In fixed point representation, a fixed number of bits are allocated to represent the integer portion of the number, and the remaining bits represent the fractional portion. This approach allows for precise calculations while avoiding the overhead associated with floating point operations. While fixed point arithmetic requires careful scaling and handling of overflow conditions, it offers a valuable tool for embedded systems developers seeking to optimize performance in applications demanding fractional number precision. Section 9. Conclusion. Data types, the unsung heroes of embedded systems. Data types are the unsung heroes of embedded systems development. They are fundamental to how information is represented, stored, and processed within these resource-constrained devices. Understanding the nuances of data types, their properties, and their impact on performance and memory usage is essential for any embedded systems developer. From the simplest 8-bit integer to the complexities of fixed-point arithmetic and custom data structures, choosing the right data type for the task is a critical design decision. By carefully considering the data being handled, the required operations, and the constraints of the target platform, developers can make informed choices that optimize system performance, reduce memory footprint, and enhance overall efficiency. As embedded systems continue to evolve and permeate every aspect of our lives, mastering data types will remain an essential skill for creating innovative, reliable, and efficient devices that power the future.